The heights of women in the United States have a normal distribution. I neglected to say that in this problem, but that's what these chapters are all about. So we've got to assume there's a normal distribution so that we can use the bell-shaped curve. In the middle would be the mean, which is given to be 63.6. And then a woman 62 inches tall would be over here to the left. So it'd say X for one person equals 62. And then I'm asking for the probability that the height would be over that. So that's going to be all of these people. And the next thing to do is calculate the z-score for this 62. So z is equal to 62 minus 63.6 divided by 2.5. And if you were going to use the calculator, what you should do is put the numerator in parentheses so that the calculator knows 62 minus a 63.6 is all in the numerator, and all of that is divided by 2.5. So we've got a negative 0.64 as the z-score. And then the next thing to do is use table A2 for the z-scores, and in fact the one that says the negative z-scores, and look up a negative 0.64. So here's the first decimal place, negative 0.6, and here's the second one, the 4. So you just find out where they cross each other, and that's a 2611, so 0.2611. And also notice that at the top it tells you these probabilities that you find, they're here for the left tail. So it was a 2611 that's then used for this left tail. So this part here is 0.2611, and the grand total of everything is a 100% or a 1, so that means what's left over for this side is 1 minus 0.2611, and for the z-scores you need to always round the decimal to 2 decimal places, since the z-table only goes to 2. For everything else, use 3 decimal places. So I've already got my calculator set right here in the mode to 3 decimal places. If it's not, you can just move over, hit enter, and then it's done. So 1 minus 0.2611 is a 739, or in other words 73.9%. So there's a 73.9% chance that a woman is over 62 inches tall. So in the population, if you were to measure all adult women, you should have, in theory, almost 74% being over 62 inches tall. Okay. Now, the second question is very similar, except now it's the average height for 7 women. So we would have, again, the bell-shaped curve. Again, the mean goes in the middle. The mean is equal to 63.6, and then over here is the 62. But now it's not just one woman, but it's the average of 7 of them. So then you say the average is 62, and again find the probability that it's over that. So that's all of this. Next step is the same thing, find the z-score. So take the score of 63, take the score of 62 take the score of 62 minus the 63.6, and then that gets divided by the standard deviation of 2.5. But then the difference is when you've got 7 people, you then divide that by the square root of the sample size of 7 people. So that's going to be, well, I need the numerator in parentheses, so 62 minus 63.6 in parentheses, and then divided by, put the denominator in parentheses, 2.5 divided by the square root of 7. And then I'm going to need 1 parenthesis to stop the square root and 1 to stop the fraction. It turns out to be 1.69. Like I said, z-scores need to be rounded to 2 decimal places, so negative 1.69. And then again, use table A2 to look up the probability. So negative 1.6, and then 9 is going to be all the way at the end. So that looks like it's 0.455. So again, this tail part is 0.455. And then subtract from 1 to get this area over here. So 1 minus 0.455 turns out to be 0.955 once you round it. Or if you like it as a percentage, 95.5% chance. So it's highly likely that the average would be over 62 inches. Or another way to say that is, if you randomly pick 7 women, it's highly unlikely the whole group is short if you chose them randomly. The next type of problem then has, again, it's back to 1 woman, but the difference here is the height is between 2 different scores, a 61 and a 68. So start with the bell-shaped curve, and the mean of 63.6 is here. 61 would be on the left, and 68 would be on the right. And the question is asking what's the probability that the height would be between these two. So we get to do the z-score twice. So we need the z-score for the 61. So z is going to be a 61 minus the mean 63.6 divided by 2.5. And then the z-score for this one would look like, take the score of 68 minus a 63.6 divided by 2.5. And then calculator time. So 61 minus 63.6 in parentheses divided by 2.5. And then do the same thing. If you don't feel like retyping it, just put second enter, and it'll give you the last problem back again. And just change this to 68. So negative 1.04 and 1.76. This one is negative 1.04, this one 1.76. And now just look up these two z-scores. The first one being the negative, it was 1.04. So negative 1.0. Okay, there's the 4 column. 1.04 will be a 1492. So this left tail is 0.1492. And then turn it over to the positive z-scores and look up a 1.76. So we'd have 1.7 and 6 is a 9608. But that's saying from that number you just looked up, 1.76, all the way to the left forever is this probability right here, 9608. So that's saying if you go from here over to the left forever, that is 0.9608. But the thing is, we want what's between the two scores. So if you take the 9608 and subtract off the 1492, you're left with what's in the middle. So then the final answer is going to be 0.9608 subtract a 1492. $96.08 minus 1492 is 0.812. So 0.812, or again you can put the percentage, 81.2%. Then for the fourth type of problem, using the table A2, this I like to say is using the table backwards. With all the other ones, you're given a score, you find the z, and then find the percentage. Well, this one's going to work backwards. We're given the percentage, work backwards to find the z, and then work backwards from that to find the score. Here we go. So this time we're given the area. So the middle is still the mean, 63.6. And the top 7% would be these tallest women here. So this is the top 7%, and we need to know what z-score goes there for that cutoff. Well, in order to find that, you then say, well, if this is 7%, then this side is 93%. The reason I need that is because this z-score is on the right-hand side, so that means it's a positive z-score. With a positive z-score, I'm using this, so I need to know what's the shaded area on the left. Now, look through the table and see where is it closest to 93%. So it looks like this one is pretty close. This one is off by 0.0006. This one's off by 0.0008. So actually this one is closer. Okay, here's where we're going to use the table backwards. Now go back over this way and find out the z-score is 1.48. So the z is 1.48. And now I need to go backwards from that and find the x. So what you could do is a little bit of algebra. You could say, well, I found out if I do the z formula, not knowing what x is, so I'd have to say x minus the mean divided by the standard deviation turns out to be a z of 1.48. And then do a little bit of algebra to solve for x. So cross multiply by a 2.5 and then add the mean. So it's going to be the mean and then plus the 1.48 multiplied by the 2.5. So I'd first multiply this over here and then add the 63.6. Or on your formula card, you can write down this is the formula, the mean plus the z-score times the standard deviation. And then let's see how tall that is. So it's going to be the mean plus 1.48 times 2.5. So that would be 67.3 inches tall. That would be a little over 5'7". All right, now we're on to the second page. Well, with the second page, the first thing to do is create several confidence intervals. Sorry that's so jumpy when I do that. And you can use your graphing calculator to create these intervals for you. Part of the reason of having the calculator is so that it can do a lot of the statistical crunch work for us. So you go to Stat, move over to Tests, which is a lot more than tests. I wish they would call it something else, but anyway. And then starting at number 7 are the intervals. The general rule is if you only have the S for the standard deviation, then use the T interval. If this over here, 4.5, happened to be the sigma, the standard deviation for everybody, then we would be using number 7, the Z interval. So use the T interval, and if you have raw data in a list, you can use the list. Here we don't, we have statistics. So we need to tell it that the mean is 35 years old, the standard deviation is 4.5, the sample size for all of these is 40, and then the confidence level for the first one is 0.90, and then create the interval. So this then says, well, at this company, it seems that the average age is between 33.801 and 36.199. And I'm 90% confident that if we ever did find the actual mean for everybody at this company, that this interval is right. Okay, now do the same thing. So go back to Stat, Tests, and it's number 8. If you don't want to scroll down and you remember the number, you can just type the number and it'll take you right to it. So the only thing to change on this is, what if we change this to be 95% level of confidence? And then calculate, and the numbers are going to change just slightly. So this is now a 33.561, and this a 36.439. And we'll explain what's happening in just a moment. So now go back and use 99%. There we go, 99%. So go over to Test, and it's number 8. Everything's the same except now this is 99%. And again, the numbers change just slightly. So now it's going from 33.073 to 36.927 years old. So then what's happening? Well, the first one goes from a 33.8 to a 36, essentially 0.2. So that's the 90% interval. Then for this one, it gets smaller, which means that on the number line it would move to the left. Only by a little, but it would move to the left. And this one gets slightly bigger, so it goes over to the right. So the interval is actually bigger. And then this one, again, this number is getting smaller, so it's moving to the left. The other number is moving to the right. So this is for 90%, this is for 95%, and this is for 99%. The next part of the question, why does it make sense that as the percentages get bigger on confidence, so you're going to be more and more confident, why are the intervals getting bigger? Well, nobody knows what the actual average age at this company is. So what we're doing is estimating. And think of the mu as a little butterfly that's flapping around in the sky. Your job is to catch it. Well, if you want to be 90% sure you're going to catch it, then just use a little net. But if you want to be 99% sure you're going to catch it, then use a much bigger net, and you've got a much better chance at catching it. So that when it finally comes falling out of the sky, then this larger net was able to catch it, so you're more confident that you're actually going to catch the mean in between those two numbers. On to the other confidence interval. So this one is about proportions. So again, use the calculator, make a 95% confidence interval. So go over here and scroll down to intervals, and now look for proportions. So it's going to be this one, letter A, 1 proportion, z interval. With proportions, you never have a choice between z and t. For proportions, everything has to be z. So 1 proportion, and this is the proportion right here, 27 out of 30. So you tell it, well, 27 of the surgeries were successful out of 30 patients. And all of these are going to be 95% level of confidence. So it turns out that the proportion in general for this particular surgical method is between 793 and 1.007. And then just do this again with each group. So you go to stat, and then A, and then this one is 36 successes out of 40. So this one is narrowed down a little more. So from 0.807 to 0.993. And then for part C, it's now 81 patients successful out of 87 surgeries. So that one goes from 0.878 to 0.984. And then for the last one. So the last one is 130 successes out of 143, and because of the larger sample size here of 143 patients, the interval here is smaller than any of the others. So this is the most narrowed interval, basically narrowing down the results between essentially 86 and 96%. So then out of these 4, if you were the doctor that had experimented with these 4 methods, which would you report to journals, medical journals, saying, I think this one is the better method? Well, I would say that if you're talking about surgery and cutting into somebody, you should probably have the most evidence possible. So I would say D, because the N is largest. If it was perhaps some late night TV scam, then maybe you should use that one and say, we have over 100% success rate, which isn't possible, but it's sort of funny. All right, on to the last part of the review here. So you've got this data out of the smokers, and here's the non-smokers. So test the claim using a 98% confidence interval that over 40% of smokers have been divorced. Well, if you've never seen this part before, that's because I'm trying to sneak in a little bit of the next chapter, but it goes like this. So really just make a confidence interval for the smokers that have been divorced. So here's the smokers, and for proportions you need 2 things, an N and an X. So we've got an N out of 485 smokers, and then an X, which is 238 have been divorced. And then make the 98% confidence interval, again, using the calculator. So go to A again, 1 proportion interval. One thing you've got to watch out for is it's very natural to write, here's how many people, N, and here's how many do whatever have a divorce. But the calculator has them switched, so make sure that you switch them back. So X is 238 out of N is 485. And in the directions, I asked to use a 98% level of confidence. So then calculate. So it's, whoops, sorry. So it is, for those people that smoke, it is a 438 to a 0.544 chance of being divorced. So it looks like somewhere around 50% plus or minus a few percent on either side. So then comes this test the claim idea. So when someone says that the rate is going to be over 40%, well, yes, that seems to be right, because according to this, it's at least 43.8%. It might even be in the 50%. So yes, the percentage or the proportion is over 40%, just as claimed. Okay, now do the same thing with non-smokers. So again, write down the essential information like N is equal to the non-smokers, and X is how many have been divorced, and create the confidence interval. So X is 374 out of 1184 for the N, and again use 98% confidence level. So that one is between 284, and P proportion goes in the middle. To the other side, 347. And then do the same idea. Test the claim that it's exactly 40%. No. In fact, according to our interval, it's going to be below 35%. No. It seems to be below 35% divorce rate. And then finally, for this last part, what do the results indicate about smoking and divorce? Well, this says for the smokers, their divorce rate is over 40%, might be as high as 50%. And for the non-smokers, their divorce rate seems to be below 35%. So it seems that people that smoke get divorced more than non-smokers.